After all this groundwork in quantum mechanics and classical computation, we can now start to convert quantum systems into platforms for quantum information processing. In this section, we are going to introduce the central notions of a quantum bit and a quantum gate. For quantum bits, we are first going to discuss how this generalizes the notion of a bit. So this really concerns the definition of these objects. And then how this really differs from a normal bit, which relates to the superposition principle and results in the notion of parallelism. Then we ask the question how much information is really stored in such a quantum bit, and how this relates to entanglement. And for the quantum gates, we again start with definitions, namely of unary and binary gates. And then we already discussed some very simple but instructive compositions of such gates. So very fundamental quantum circuits, and these illustrate how we can generate superpositions and entangled states. Also how we can actually utilize entanglement. But there we can also illustrate one of the key limitations of quantum information processing, which is expressed in the no cloning theorem. So these are the key aspects of this chapter, and we are going to start with quantum bits. So let us start with quantum bits. Well, physically, a quantum bit is simply a quantum mechanical system with two levels of exactly the kind that we discussed in great detail in the background section. So quantum bits are two-level systems. So each of these bits corresponds to a quantum system with two fundamental states, which we assume to be orthogonal and normalized. And we label them again as 0 and 1 with amplitudes alpha and beta. So we can also interpret them quantum mechanically simply as a vector in this specific basis. Now the key idea is that we are going to interpret these two specific states as the states of a normal bit with values 0 and 1. These quantum bits we also call qubits. So whenever we find this physical system in these particular states, then we say that they represent these specific states of information. And because of this, we call this specific basis the computational basis. So whenever the system is in these specific states, we are going to interpret these as definite states of information. But being quantum systems, we also have to allow for the fact that the system is in one of these superpositions. Now this will be very useful, as we will see very soon. But just let me mention that we can of course then still force the system into one of these definite states by doing a measurement. And in these measurements we would read out the values 0 or 1 with the probabilities alpha squared or beta squared, assuming that the quantum state with which we work is normalized. Now with these values 0 and 1 as the readouts, this corresponds to a very specific measurement observable, which I just write down for completeness. We can write this in terms of the identity matrix and the Pauli Z matrix. And as a 2x2 matrix, it simply corresponds to this observable here. So this is a diagonal matrix with entries 0 and 1 on the diagonal, and these are then the eigenvalues that we can observe in the experiment. And the corresponding eigenstates are simply 1, 0 and 0, 1, which simply correspond to these two different states, so the states in our computational basis. Now it is very important to point out that the idea of quantum information processing is not to store information directly into these numbers alpha and beta. If we would be doing this, then we would be more close to an analog computer. So the idea is different from an analog computer. And the reason is that when we do these measurements, even though we obtain some information about alpha and beta, we change the state into one of these two states. So our next measurement is not going to give us any further information about these numbers alpha and beta that we had in the quantum state before we did the first measurement. So nothing is gained from these additional experiments in terms of finding out what alpha and beta are. You could take many similar copies of the same system and do many of these operations, but this of course would simply amount to a precision measurement of these probabilities and would just take a long time, so this will also not be the resource that we want to exploit. Instead, we want to use the superpositions and indeed also entanglement, and we see how this becomes useful when we simply look at a system which has more than just a single qubit, so a so-called register of, say, n qubits. So let us look at a system with n qubits. So physically this is now just a composed quantum system, but in terms of computations, this is now a system that can store more of this information in computational basis states that we can enumerate in the following way. So these are just the different states of the n qubits enumerated from 0 and n-1. So these are the indices of the different qubits. So therefore each of these entries can take the value 0 or 1, and each of these entries can do this independently. So altogether we will have 2 to the n states, and I'm going to abbreviate this by a curly n, and this symbol with this interpretation will occur many times in the remainder of this course. So this again we would call the computational basis. And we would again say that these computational basis states represent states of definite information encoded in all of these values here. Now we can of course interpret all of this here as a binary number. And this number I'm going to call x, and it would therefore just be given as the following expression with all these binary digits or bits multiplied by powers of 2. And then we can of course just enumerate all these computational bases also by this integer x, which is simply running from 0 to 2 to the n-1. Now these are the computational basis states, but we can of course also consider general superpositions, and these we could now write for instance as a sum with amplitudes psi x summed over all of these different states, and this would then run from x equal to 0 to 2 to the n-1, but this we can now of course just write like this, and this is one of the reasons why we introduced this symbol, because it will simply appear so many times. So these are now superpositions of all these computational basis states, so they are not definite states of information, but we can again convert them into these, say by a measurement, where we measure all the different qubits by the same type of measurement which I just described, and then we will obtain different results here, and the probability that this corresponds to the integer x will simply be given by the absolute value squared of this corresponding amplitude psi x. Now this again assumes that the state is normalized. Now these are again no longer states of definite information. Now we have all these probabilities, but nonetheless these superpositions are the key resource for quantum information processing. And this is for two reasons, and the first one is that they're just superpositions. For instance, we can consider the following particular state, which I'm going to denote as capital psi, and what I'm going to write down here will be a state that we will encounter many times again in the remainder of this course. And this is simply the state in which all the computational basis states occur with the same probability. So because there are curly n states, the corresponding probability amplitude would be 1 over the square root of this. Hence, when we square this number, we will get 1 over n. So all the different states, all these numbers x that we can read out, will simply occur with the same probability. This is just one example of such a state, because these probabilities are really the absolute value squared of complex numbers. So there could be arbitrary phases, but this is really the simplest one. Now it happens that this particular state which I've written down here, this very important state capital psi, is indeed separable. It can be written as a product of states of all the individual quantum bits, and they are all in the same identical state. So this is just a product of all of these states, where they are simply individually in the superposition of the states 0 and 1, with equal probabilities of these two computational basis states for each individual quantum bit. You can see this by simply multiplying all the terms out, and then you will get 2 to the n different terms, which all differ simply by the selection of the entries 0 and 1 at the different places where these numbers xn appear, the different bits that really enumerate all the different states. And now we see that the state represents all these numbers at the same time. And this could be potentially a very large number, given that this curly n here depends exponentially on the number of qubits. Now this is not a definite state of information, so this may be not a useful state at the end of a calculation, but it may be very useful in the middle of a calculation. For instance, when we want to test some properties of these numbers. This is indeed one of the key ideas of quantum information processing. We call it a resource, and this specific resource we call quantum parallelism. So in general we deal with superposition of many states, not only in this form, but simply also in this most general form, and this we call quantum parallelism. So this is one reason why these superpositions will be useful for computations, but there is another one, and this is simply entanglement. And in order to see how this enters, it is useful to ask the question how much information we can store into a single quantum bit.